Мне что-то показалось, что это я послышала. Вспомнишь, что солнце слышала ее разговор. Сразу. Не, может, и я. Может, я...
Там, если что-то понюхай, будет видно. Слушай, а что там из колонки кто-то доносит? Нет, да, там, скорее всего, наверное, кто-то присоединится. Михаил вчера тоже говорил, может, я часто каждую всю лекцию.
А подожди, есть уже? Вот я не помню, как это докладчик на занятии было.
Что-то смотреть надо?
Потому что сейчас их видно на экране, а мне это не нужно. И именно для зума я тогда тоже с этими самыми, со студентами никак не могла найти. Да, может быть, опять. Сделайте мне заметки, чтобы я говорила, а не думала, что я сама. Мне просто эта лекция вообще не откатывает.
Надо...
Есть проблемы нельзя решить, так нельзя, но вообще обидно. То есть одно показывает, второе проверить? Не, нормально. О, все, супер. Вот, но они не везде просто есть. Не, они просто у меня на тех пар, которые у меня тяжелые. Ну да.
Интересно. Причем вот это видно заметно совсем. Его нужно прям получается ровно. Нет, настройки. Это настройки. А его нельзя?
Целиком.
Смотри. Ну, короче, да, все нормально. Сейчас еще немножко его улучшу. Все, ровненько.
Мышкой, да, просто?
Есть кликер. Куда он делся? Можно просто мышкой, да.
Я просто мышку.
Hello, dear kids.
Hello.
So today we will start our day with the presentation made by Dr. Natalia Kuzmenkova, and today it will be about radionuclide migration, behavior and weights, and what we should to control to estimate the migration behavior of radionuclides in the environment. It is essential part of any decommissioning project or radioactive waste management, because for safety assessment we have to predict the migration behavior of radionuclide. So it is always a very important part. So please, Natalia.
Hello, dear friends. As you said, my name is Natalia Kuzmenkova, and I work here in radiochemistry division, chemistry department. Last time in summer, I told you about monitoring, environmental monitoring around nuclear facilities and nuclear power plants. And really, in your program, the lecture should be the same. But as I understood, a lot of people here already heard that lecture, and that's why we changed a little bit the theme of my lecture. I'm working here and working with environmental radioactivity. My work is closely connecting with the sampling all over the world, but most of Russia territory. I visited, I think, all nuclear facilities in Russia, and the most of dangerous radioactivity places in the world, like Fukushima, Chernobyl, Semipalatinsk, and others, and everywhere me and my command, we took samples and analyzed here in radiochemistry division. And now I will show you how we are working with environmental samples to understand how radionuclides are mobile, and about radionuclides bioavailability and other things. Okay, let's start. Radionuclides migration waste in the environment. I think this simple scheme for you to understand that the aim of all radionuclides environmental radioactivity investigations is because of human, because of person, and for us to understand how radionuclides is going and achieve the goal that humanity and how it will affect. This is a very simple scheme. Most of radionuclides, most part of radionuclides have gone to the planet from atmosphere because of radionuclide explosions and accidents and a lot of other reasons. Radionuclide sources. For you, I think it is not the news, But just to remember one more time, to understand one more time that the radionuclide sources can be natural, artificial, and technogenic. And natural sources divided to cosmogenic rocks, and artificial radionuclides is going to the planet because of nuclear explosions, medicine and science, nuclear facilities, and radioactive accidents. And for example, here in radiochemistry division, every day we produce a lot of radioactive waste with very, very low activity, but all of that radionuclides are also can go to environment. Just also very simple information to you that in the Earth exists three mother radionuclides, thorium and 2 isotopes of uranium, and all of other natural radionuclides, they're just daughters of that three. I'm sorry for Russian language, but after the Fukushima, all of you, I think, know about that. In 11 of March 2011, a lot of radionuclides was going to the planet, and because of the wind, it spread all to the planet surface all over the world. And in Siberia, for example, in Tomsk or Krasnoyarsk, scientists found out radionuclides from Fukushima because that radionuclides made the circle around the Earth. Yes.
Thomas.
Tomsk?
And
Yeah, maybe you know about
there
that.
is radioactive near from us, and there is also 2 reactors in the university of that. It's a very
This information I understand that everybody you know that, but first of all, it's yeah, the school of radiochemistry, and after I will I'll say well how we can analyze. But you must understand that you can find radioactivity in the artificial radionuclides everywhere, and you can find Fukushima radionuclides everywhere. Nuclear power plants in the world, most of them are located in the North Hemisphere. That's why North Hemisphere, where we are now, yes, the most radioactive contaminated part of the world. Russia, as I said before, has only 11 nuclear power plants.
11?
11, that's it. It is very confused, but it really it's true. 13, 15, United States, Europe, Japan, but the biggest country in the world, yes, 11 nuclear power plants.
How many be honest?
In Russia now,
Yes.
no one.
One under construction. Under construction. What is it?
Destructed.
Commissioning.
Commissioning, one, I think, Obnest. One nuclear power plant to commission. It's very close from Moscow, Obnest city, and that nuclear power plant decommissioned.
This is was the first nuclear power plant in the world.
Yes, the first nuclear power plant in Russia. And some of nuclear power plants repaired. For example, in Smolensk, in Kursk, as I know, nuclear power plants now repaired, reactors changed. But nothing constructing from nothing new, no new nuclear power plants. Russia constructing power plants all over the world, but not in Russia. Russia constructing yeah, in Bangladesh, in Uzbekistan, and Turkey, and other places. Yeah. But not in Russia. Nuclear accidents, incidents, and radiation accidents. Just because of nuclear facility located in the North Hemisphere, the accidents and incidents also are occurred in the North Hemisphere. And that's why we have a lot of work now. For example, longitudinal distribution of plutonium, two isotopes of plutonium allow due to nuclear weapon tests in the atmosphere. You can see that the concentration depends on latitude. And that information, I think, also very important, first of all, because you can find plutonium isotopes everywhere, and in South Hemisphere as well, and in North Hemisphere, everywhere, and in every sample. Everything just depends on the method how you will analyze it. Very, very sensitive method can find plutonium isotopes in every sample that you can take. Okay, challenges in radioecology, linking radionuclide species in sources to impact and risk assessment. Our thing, radionuclide migration ways. As I said before, everything, most part of radionuclide migration in the world depends on source. And the form, physical chemical form, or the existing form depends on the form in which radionuclides is going to the surface. And after that, transport in different ecosystem depends on climate conditions, soil, water, sediments conditions, and all of these affect to bioavailability of radionuclides and uptake. I think we understand, but I'll just repeat one more time, that radionuclides can be present in different physical chemical forms, influencing transport, mobility, and bioavailability. And it depends on source and release conditions and transformation processes. But the source is the main, the most important factor for, of course, first of all, artificial radionuclides transport in the environment. Association and fractionation techniques are needed to distinguish between radionuclide species. And I will tell you about this and what we used in radiochemistry division. Three most important form of radionuclides: dissolved, colloid form, and migration with particles. For radionuclides, we all of us well know, but sometimes it is difficult to separate radionuclide forms for one of these three titans. And because of that, radionuclide migration is very, very affected. You can see biological uptake, pore water, absorption, physical, electrochemical, mobile fractions associated with the redox sensitive phases and hemisorption, and bondage and mineral structure. For good investigation, when you're working with environmental samples, it is better to understand all these blocks. how count which number of radionuclides are really biological organisms cannot take. It is very important to separate pore water from sediments when you are taking contaminated sediments from reservoirs. And you should understand sorption mechanisms and which part of radionuclides don't migrate in mobile form, are just bonded in mineral structures. And also these type of radionuclides also can migrate, but with particles. For example, with wind, with water, and this physical chemical form of radionuclide, really it is the most important now in the world, because particles, and exactly the what particles, affected very, very strong for humanity and for animals. Under various release scenarios, relaxation behavior is even more complicated. Source depends, source independent, pseudocolloid, intrinsic colloids, and hot particles. Maybe you know that colloids transport of radionuclides is most important for biota, because only with this way biota can uptake radionuclides. Sometimes with hot particles, but the most important way is colloid way. You understand these differences, yes? Just the colloids is, for example, dioxide of plutonium, yes, and colloids. Oh no, it's not true. Instead, colloids is dioxide of plutonium, and some colloids, and when plutonium is just stick on my complex with other colloids, not plutonium colloids. Okay, speciation of radionuclides. It's very inconvenient, really, to. Okay. Speciation depends on diameter of particle and molecular mass. And you can see here that differentiation, category and classes. And the method, how you can determine total activity first of all, and after that specified the size of your radionuclides and the size with which form your radionuclides will move. And you can see here the differentiation that is now in radioecology, all specialists using this differentiation. Okay.
Doctor, please would you mind to illustrate the previous slide again?
Yes.
Excuse me. What's the meaning? What's the meaning of interesting colloids?
As I said before, a colloid that creates radionuclide. For example, plutonium dioxide is intrinsic colloid, the true colloid. And when plutonium or other radionuclides stick or make complex with already existing colloid, it's pseudocolloids. And the radionuclide options, some radionuclides can make it true colloids, and some radionuclides cannot.
Based on what? Based on what?
What?
What's the basics to migrate or not again migrate?
More important that it affected by bioavailability. Radionuclides can migrate, as I said before, in dissolved form, colloid form, and migration with particles. These three types of radionuclide migration in the environment that everybody should know. But it is only three, really three types. And this dissolved form and colloid form, its effect for bioavailability of radionuclides. Radionuclides can go inside the cells, for example, just in dissolved and colloid forms. When the radionuclides migration with particles, it is physical solution. It is also very, very important because particles are the most radioactive compared to colloids and dissolved form of radionuclides. But for viability, the most important forms are dissolved form and colloid form. And colloid form separated per two, true colloids and pseudocolloids. True colloids, it's colloids that radionuclide can create itself. And pseudocolloids, it's already existing colloids in which radionuclide just make the complex and migrate together with existing colloids. Colloids, pseudocolloids, particles, and simple compounds depends on the size, the diameter, and molecular mass. And this, as I said, this differentiation is already is used by every radioecologist now in the world. Definition of particles in water, sediments, biota. It is the previous picture, but in words. Fragment larger than 2 millimeters, particles size 1 inches. Sense, silt fraction, colloidal, nanoparticle size, low molecular mass species. Okay. Hot particles. The migration form with particles. Here I just want you to show sources which produced a lot of hot particles, most of hot particles in the world. It is particles released during nuclear weapons test, nuclear reactor accident, nuclear accident involving satellites, conventional detonation of nuclear weapons, and particles released from nuclear installation. Why it is important? Because all these particles have different compositions. And if you see the particle composition, you can find the source of that particle. All these particles nowadays analyzed, and all composition are clear. And for example, if you in Tomsk, for example, you can find some particles and you analyze the composition, and you can understand that the particles from Palomares. Yes, Palomares, just because someone went to España for vacations, and on the shoes can take to Tomsk hot particle. It is really works now.
But what do you mean from nuclear installations? Do you mean the field cycle or for commissioning? Why particles released from nuclear installation?
What I mean, it is
because normally all the steps are safe, and normally it shouldn't be any release, right? While doing there's only release. There's always a limit for release, but the
Yes.
facilities, they are allowed to release. Yeah, but during the installation. So from nuclear facilities, installation is like facilities.
It is facilities, yes, exactly.
Ah, okay.
It is facilities.
Yeah, okay. Sorry.
But of course,
My misunderstanding.
I agree, and of course, every nuclear enterprise produced radionuclides in normal condition, normal explanation, yeah.
Acceptable dose.
Yes,
Yeah, okay.
acceptable dose, but produced. But here, of course, yes, I mean facilities. Certificate and condition determining transport of plutonium. It's I don't know, simple scheme, but just for you to understand that when you're working with environmental samples, separate radionuclides or your sample by size, it is very important because colloidal to colloidal migration way is the most important for biota, as you said before. Just when you study of environmental reactivity requires an integrated approach. I think is another theme for discussion, but which 6 steps that you should do every time you're working with environmental samples. Size and charge distribution pattern. Of course, we and everybody recommended fractionation according to size. It is very important. And separate particles and colloids. And it is possible to make this procedure in the field. And fractionation according to charge species to avoid analytical problems. I can show you how it is possible to make in the field. A series of side and charge fractionation techniques are available now for radionuclide species in water. And as for me, in general, fractionation species should take place in the field, because when you transport water or soil or I don't know animal sample to the laboratory, during the way species and the radionuclides physical chemical forms can change. For example, you can use different types of filters, and you really can separate radionuclides by size in the field. Filtration of water is most applied fractionation technique worldwide. And it is really possible now to separate colloids forms in the field, just using different types of filter. Okay, this is one part of investigation radionuclide migration way. You can separate your radionuclides by size. Another type of radionuclide migration way investigations is concentration factors and comparable different radionuclide activities in the object and in the environment where it object lives. For example, this simple scheme about radionuclides migration way to the reservoir. Radionuclides ways go to reservoir, and very fast the sorption of bottom sediment, radionuclides bottom sediments by bottom sediments is very fast. And maybe you know, because a lot of experiments, sorting experiments shows, but that the most part of radionuclides sort by solvents during the 24 hours. It really works for most of radionuclides. And after that, radionuclides can migrate to phytoplankton, zooplankton, benthos, and roach and pike. For example, fish. One fish, I forget, хищники и травоядные. Say.
Fishing это рыбалка.
Не, хищники, не хищники. Predators. This one, yes, predator fish, and this one, fish eating the phytoplankton and grass. And the migration, radionuclides migration through the eating chain is also one of the parts of investigation radionuclides migration way. All information that I give you, all these investigation methods we can use and using here in the radiochemistry department. We have all equipment to separate radionuclides by the parts, for example, in the field. We can working with any material, any environmental sample, with fish, with bathroom samples, sediments, with grass here. When you are analyze radionuclides migration in the environment, it is also important to separate biota and abiota components of environment. Because, as I said before, radionuclides is going to the environment and sort very fast, and after that it can change its physical, chemical form affected by environmental conditions, and after that it began to migrate. And it is very important to understand well in which physical chemical form radionuclides exist in abiota environmental samples. Here we analyze the phytozooplankton, fish, so benthos, and this investigation. And for biologists, how usually biologists investigate radionuclides? We investigate radionuclides migration using concentration ratio. I will show you how they do it. Okay. For example, concentration ratio or coefficient, distribution coefficient. What does it mean? It's activity concentration in solid phase, for example, becquerel per kilogram, and activity concentration in liquid phase. Usually it means with divided concentration in sediment to concentration in water. For example, here you can see the distribution coefficient for a very, very contaminated radioactive pond in Ural in Russia. But biology doesn't stop on that distribution coefficient, water to sediment, and then began to divide everything to everything. And here you can see, for example, concentration ratio when they're using concentration biota to concentration in water. And you can see that, for example, phyto and zooplankton, they also rapidly absorb radionuclides from water, and maximum concentration ratio revealed for americium and plutonium and cesium. And phytoplankton accumulates radionuclides better than zooplankton. And it just because phytoplankton has the surface square higher than in zooplankton. We as chemists, we can analyze biota in the view of chemists. And really, when we saw this distribution, why phytoplankton accumulates more than zooplankton, it's just because the surface square of phytoplankton is small, yes, and zooplankton bigger, and that's why the surface square higher, and that's why it accumulates more. It is very simple, but it works. And biologists agree with us because, okay, maybe.
Sorry, what does the indication? R17 or R4?
It's different reservoirs from plant Maya. Just for example, maybe you know that plant Maya has the cascade of reservoirs, which are really radioactive waste storages now, and different ponds collect different level of radioactive waste. And here we investigated two reservoirs. 17 is the most contaminated pond in the world, reservoir in the world, and the reservoir number 4. It is not so contaminated, but more interesting for investigation because we took from there a lot of types of environmental samples, fish and planktons and others. And it was very interesting work because the activity is very high, and that's why analyzing samples is very simple. Just put into the water and you can analyze water. You no need to concentrate because the activity is very, very high. But this concentration ratio or distribution coefficient way is very biological way, but it shows a lot of bioavailability of radionuclides. And using just activities and divide 1 to 1, you can understand the bioavailability of radionuclides. For example, for that reservoirs americium shows maximum bioavailability.
And I have a question about that. About cesium. Does this zooplankton absorb the most cesium?
Yes,
Yeah.
yes.
So you can explain.
We explained this because of
Because strontium is not so clear.
yeah, we have a lot of questions with strontium here. Yeah, and we think that it can be some residual fraction of strontium in that pods, but it is another thing. About cesium, zooplankton accumulates and phytoplankton accumulates. I will show later, but here the mechanism of migration was particles, and the particles of bottom sediments just stick on the zooplankton and phytoplankton surface, and that's why affected a lot to the biota. And I think that's why here is so high concentration ratio. It is it was real work. We investigated that, and now this work is continuous, and we're trying to understand what is going on. And this work, as I said, continue. The problem here is that Mayak radioactive reservoirs are working now, and the radioactive waste is going there every day, and nowadays it is continuous. And we cannot be sure in what form exactly radionuclides are going with the liquid waste. And sometimes I think it can make a big mistake for our investigation and understand the real situation.
Do you use gamma analysis for determination?
Gamma
Gamma, how you measure gamma? Strontium.
depends on radionuclide.
Yeah, I know the physicist because I asked strontium is impossible to measure by gamma.
Of course, depends on the radionuclides, of course. And plutonium and uranium,
Yeah.
of course, we use alpha,
Strontium is not possible.
strontium, beta, yes, of course.
Cesium by gamma.
Cesium, cobalt, and also americium by gamma. Americium has line 59, yeah. And of course, we separated
All of that. but
plutonium, uranium, and strontium from biota using air-chrome cartridges, using
okay.
resins, Teva, strontium resin. Yeah. Of course, it was a very big work when we took really small zooplankton, yes, and because the activity was very high, we have a possibility to measure and to separate plutonium from zooplankton. Because of that, we are working with that reservoir. But it is really difficult to understand waste because we don't know the composition of liquid waste. And as I said, the most important is the source. We hope that someone that reservoir will stop works like storage, and we will find out what is going when the after that period, and understand exactly in which form radionuclides and can forecast radionuclides physicochemical forms will be changed or not. But nowadays, this way, the concentration ratio way, is the most popular in biological community. Yeah? For example, as I said, biologists divided everything to everything. For example, its concentration factor thermometer to water, and pyramids to sediments. And this is radionuclides line according to concentration ratio, just for that radioactive waste storage. Also maximum is in americium and minimum plutonium.
Is there any clarification about this output, or it is just observational output?
Sorry, could you repeat?
Why maximum?
Why?
Yeah. Is it observational output, or there is a region behind this?
No, I think it's just because of radioactive waste composition output. Yeah.
So it's the observational output.
Yes. Okay, concentration ratio in fish. And when you're separated everything to everything, everybody, of course, you should understand why it occurs. And we continues in our investigation and use the digital radiography for understand the form of radionuclide and to determine the radionuclide micro distribution in hydrobelts. The sample were analyzed by radiography using imaging plate. I can repeat that everything, any equipment we can have here, we have here in the radiochemistry division, and really we saw uneven distribution of radionuclides in the laboratory surface, and also we saw uneven distribution on the leaves, on grass, and it looks like the hot particles. But we analyzed these using scanning electronic microscopy, and we saw that that is not hot particles. That is just bottom sediments that sticks on the surface. Yeah, and radioactivity related with the material deposits on the permanent surface. It's elemental composition. We understand it. You can see it. And what does it mean? It means that particles, hot particles, or the residual form of radionuclides can affect biota more than soluble and colloidal form. It doesn't goes inside the cell or inside the organism. But when contaminated on the surface, it can affect more high than other radionuclides migration ways. Okay, radionuclide species are defined according to their physical-chemical properties: molecular mass, charge properties, oxidation state, valence structure, complex ability. And which equipment, which ways, which analysis you can make to understand their radionuclides mobility, their radionuclides physical-chemical form. Of course, you can use alpha-threat analysis to search the hot particles, scanning electron microscopy for morphology, major element composition, SIMS, and the XRF, SANS, XRD, everything you want. I will show you how it works.
Does this department have SIM?
Exactly, this department not, but we have collaboration with a laboratory very close from here that making SIMS analysis for us.
Very expensive.
We have a collaboration, and it's not a problem. But usually, you should understand that radiochemical division is not an analytical laboratory. We are working, we're investigating samples in very small amount, and that's why for laboratories it's not a problem to have collaboration with us, because we will not give them hundreds of samples. Yes, I just asked to analyze one thermometer. Yeah, it's not a problem, and we will understand environmental process clearly and publish good article. That's why for us it's not a problem. XRF we have here, and most of this we have here. Scanning electronic microscopy we have here, transmission electronic microscopy as well. For example, how it works, alpha-threat analysis. First of all, we are looking for alpha-emitted hot particles using alpha-threat analysis, because it is very cheap, not very expensive, and simple to make the analysis. Using alpha-threat analysis and this radiography, autoradiography analysis. Further characterization with XAFs and SAM. For example, here you can make the elemental mapping of your sample. And transmission electronic microscopy, as I said, we have here on radiochemistry division, and we use to analyze, as I said, alkaloids, for example, of plutonium and plutonium dioxide, and we can see it using transmission electronic microscopy.
So this your department already has established this platinum and investigation lab already established. You have a huge fund on the government, the colleague, but is it the lab established already?
What? We have all this equipment and we can use it. Huh?
Spectroscopy lab for platinum.
What spectroscopy? I don't hear well.
Okay, maybe
Sorry. X-ray absorption spectroscopy, XANX and EXAF. We have no here in division, in radiochemistry division. It's located on the Kurchatov Institute, but we have a collaboration, and we're working with them very, very close. A combination of different analytical tools can be very powerful, and I think you understand this. Okay. Example of source dependent species. Alpha emitted radionuclides are located in discrete particles and different particles. For my experience, for example, I worked in Chernobyl, and as well nowadays we found different types of hot particles in Chernobyl territory. And it is interesting that investigation doesn't stop, and it continues because the hot particles change the composition, and really we don't understand, but because of time, of course, only time and environment effect to that. But for example, we went to Chernobyl 2 months ago, and we found new types of hot particles there. Really interesting.
Which types?
Which types? It is was americium particle without any cesium and plutonium. No, only americium. Was interesting, but of course it depends on the rates.
Yeah, this is the sort of the decay of the reaction.
That's like, I mean, it's from 400 years cesium free.
Of course, 30 years left, but 35 years left. But before, the activity of cesium was 2 or 3 levels high, and the just half-life period cannot decrease the activity so much. We understand that, yeah. But now we found only americium.
Just one half-life.
It is just one half-life, yes, of course, and cannot decrease the activity levels. Okay, sorption mechanism important for mobility. For you to understand physical sorption, electrochemical sorption, and chemisorption. I just to combine all information for you to be clear to understand that it is only 3 forms. And sorption, really, you can combine all sorption process to these three types: physical, electrochemical, and chemical sorption. And in the end of my presentation, I just want you to show this slide. Our division is working a lot to understand the sorption mechanism of radionuclides, and we are dealing with and working and making sorption experiments every day. We have a very, very strong group, sorption group here, that are working to understand sorption mechanism. As you understand, for example, to make exapsate and xenos analysis, you should have a very, very high concentration of radionuclides. And these analyses are, most of all, are impossible to make with environmental samples. But when you are working with modeling experiments, it is possible. And to make modeling experiments is one of the most important part to understand radionuclides chemical sorption mechanisms. And I really understand that it works in different ways, but in another hand, all radionuclides are putting in the environment, like we in laboratory put radionuclides to our environmental sample or object. The way is the same. Most important is, I think, time. Yes. And of course, in laboratory, it is impossible to wait 35 years. But maybe we can make the process quickly, I don't know. Okay, that's it. Thank you very much.
Questions?
Но у нас была дискуссия, we had discussion during the election.
Then we can have a 5-10 minutes break, and then we will continue.
Наталья, скажите, вы отличаете, вот, скажем, изотопы, как 243 миллилитр или 241 миллилитр, что вы находите?
241 ногами находим, 243 альфа.
Ну, вы говорите, нового типа, то есть изменился изотопный состав?
Про частицу?
Да, при горячей.
Да, соотношение изотопов изменилось.
То есть раньше, вообще интересно, да. То есть раньше была обнаружена горячая частица с большим содержанием цезия, в том числе, то есть и горячая не потому, что там топливные частицы трансурановые именно, да. А сейчас, значит, цезия практически нет, осталось одни трансурановые элементы. Но все равно это тот же самый америций, не какие-то другие, да, вы вдруг начали находить.
Да, мы еще пока ее не растворили, мы пока сделали только неразрушающий анализ и увидели вот это. Но мы сейчас ее растворим, посмотрим, что там дальше.
А какие методы фильтрации, вот, чтобы эта дисперсная частица распределиться там от единицы нанометров, от 2, как я видела, прям до полмикрона? Да. Какие методы фильтрации используют?
Ну, набор фильтров, вот, у нас есть какой-то готовый набор. Там 100 дальтонов.
Начиная с 450 нанометров до 10 килодальтон, то есть 2-3 нанометра в диаметре. То есть последовательно через фильтры фильтровали, новые фильтры.
Понятно.
И потом анализируется содержание.
Просто я говорил, да, что мы делаем это в полевых условиях, очень удобно и важно.
И еще вопрос, я на прошлой не была в школе, а можно мне ту лекцию, которая была
про мониторинг?
Да, про мониторинг.
Ну, можно, конечно.
Сейчас я тогда флешечку.
Но она у меня сейчас с собой-то нет.
Мне кажется,
Да?
Еще же будет у вас лекция,
У
по-моему?
меня, наверное, завтра практикум с вами будет.
Очень хорошо.
Вечером.
Ну, тогда завтра. Хорошо.
So we will see each other again. Yes. So this is my card. I'm from Serbia. I'm the professor of nuclear physics, and I'm teaching environmental radioactivity and in radiochemistry. I am very interested in, but we do not have a good.
Yeah, so you are going here because it's cool.
Yeah, it was okay. For me, of the commission, etc. So what I will see tomorrow again, but I'm thinking about some Erasmus collaboration. Are you in the
Oh, of course, I know
Erasmus?
about that program, yes.
Yes, maybe it would be useful to make it through our university if it's not starting. I'm thinking about some joint master programs with us.
Yes, yes, yes.
This is my
Be in touch.
card, so we can be in touch. It's very nice presentation.
Thank you for the nice presentation, guys. My work is based on this scope area. I choose nanomaterials and nanomaterials, frameworks, and so on for novel project produced. And basically, I have a research proposal, but I can't advise them because I haven't listened about lithium. How to
Tritium?
lithium.
Ah.
Yes. Have a nice proposal. You have abilities for lithium. We can
Yes.
make it with lithium.
Yes, 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 of course we have.
Because
Because, yes, of course, yes, we have a liquid oscillator counter, we have
it's a beta emitter. Beta emitter.
yes, beta emitter with a very low energy about
I have a very nice proposal about a small cavity metal organic frameworks. Small cavity based on the size of lithium. Because lithium in the water is a problem in Fukushima. Fukushima. So a company 9 Sigma sent to me an email. They need a suggested research proposal according to my recent publication. It was about manganese and coal. So they want from me suggested research proposal. Already I make the research proposal about this subject, and I'm so excited to start it. So we can make like cooperation. I have a
it's
material
not a
in
problem.
Egypt.
Yeah,
I can to give you the material and then make cooperation. Why not?
yes, yeah, why not, I agree with you, but we can try. Tritium is very difficult, really difficult, because it has different forms.
This is my card first one.
Okay.
Hassan Alam and my Google Scholar.
Tomorrow I will give you cards.
Okay. Why not? Tritium and hydrogen, both of them have the same chemistry. However, tritium hydrogen is faster than tritium. So if we have a contaminated filtrated water with tritium, if we pass above like membrane of my materials or waves, the hydrogen will be passed. Maybe tritium will be catched. Maybe it's
Yes, we have.
and not only MOFs will be treated with materials like mixins, metal carbides, or nanometal oxides.
Can I drink a cup?
Okay, why is
So, dear colleagues, let's continue.
So the late frozen November, and then you can walk to the south winter in December or January. You go to the south, you prepare like traditional south with firewood, and then each side the south you have a hatch, you open the hatch, inside
Okay, dear colleagues, let's continue with a short presentation and then we'll have a longer break. So just a short presentation about what we are doing here in the field of education for data machining. It will be some. So as you all already know, nuclear technologies, it's not only the production of nuclear energy. The nuclear technologies, they include a wide variety of different applications. Of course, energy production, but also it's some medical application, it's applications for agriculture, when you irradiate all the seeds, not all, but some of the seeds or fruits, you kill all the bacteria, but the properties, the taste properties, so the color, they don't change. So it is very effective. Also for agriculture, you can use it for breeding, making mutations for plants, etc., etc. So also it is interesting application for cultural heritage because many applications for starting from the dating of the some piece of arts or investigation of pictures, drawings, with X-ray techniques, etc. So nuclear or radiation technologies, maybe better to use words radiation technologies. They're used everywhere in chemistry, in industry. Applications are very wide. And but we have to remember that there is not only benefits, but some responsibilities, because it is potentially hazard technologies if you manage it not in a safe way. Also, from the past, we know that when you apply these technologies, even for the peaceful applications, finally you can result in some very bad situations like contamination of the territory, even for peaceful application of this nuclear technologies. Like it was many cases in Russia, for example, then it was a project for when nuclear explosions was used to create storages for gas or water or oil, or to intensify the production of gas ores, and etc. Or it was the mega project to change the movement of the rivers from the north direction to the south directions, and some other very strange applications, but this all resulted in the contamination of the territory. And of course, as we saw from the many cases, from the even starting from 3 Mile Island accident, from Chernobyl accident, from Fukushima accident, that when we don't speak openly and clearly to public what is happening with, during accidents, we create mistrust in public to the nuclear technology. So even in the very worst situation, my personal opinion that we have to be open for the public and explain what is happening, and not to hide the reasons and the consequences of the accidents. And nuclear facilities, as far as there are many applications, there are many different nuclear facilities, starting of course with nuclear reactors, with radiochemical plants, with mining of uranium ore. But there are research reactors, research institutes who are dealing with radioactive materials. There are transport reactors for submarines, for icebreakers. In Russia, it is now more and more developing technology to create these icebreakers to make the all-season pathway through the North Ocean. Of course, medical facilities, and of course, storages and disposals of radioactive waste. And in any nuclear facility has its own life cycle, as we saw from the lecture that was given by Vladimir Michal yesterday. It started from the planning and all the steps for design, construction, then operation, and finally decommissioning. So decommissioning is the final step for any nuclear facility, and it is important to think about decommissioning even from the planning of these facilities. This picture you already seen in my lecture, that there are plenty of nuclear facilities of different kinds will be decommissioned in the near future. And decommissioning is very complex, and nowadays it is still a problematic area, because it's more or less a new topic in nuclear technologies, because before it was not such a lot of objects to decommission, but as we mentioned already many times, that from the last century we have already a lot of facilities that are already have to be decommissioned, and this number is increasing, and thus this area of expertise will grow within the future years. And it is a problematic area or sphere of nuclear technologies because it includes many different aspects from legislation and existing technologies. Are these technologies sufficient to safely decommission the nuclear facilities or not? Should we develop a new one, and etc., etc.? It is, of course, involvement of stakeholders, estimation of finances and costs, and finally, of course, the management of radioactive waste. And there are different possible problems during decommissioning. First of all, as far as decommissioning is relatively new topic, there can be no long-term program for decommissioning, long-term policy in the country, and this can result in invalid, incorrect estimation of the costing of the time that is required for decommissioning. Also, it can result in the absence or some lack, imperfection of the legislation base. So there can be questions between different organizations who are responsible for different steps during decommissioning, because it is not always clear when you remove the facility, dismantle it to many parts, who are responsible for these parts, and many other questions. There can be problems with radioactive waste management, because you can use a new type of waste that were not previously existed in the country or in the field. And of course, at least in Russia, in USA, in some other countries, the problem of legacy. You have no enough information about the facility, about the radiological radionuclide inventory, and many other unknown problems in legacy. And as we always mentioned, it is involvement of stakeholders who are every person who are involved in the or affected by the decommissioning of these facilities, either by radiological hazard or economical changes in the region, or by other effects. So there are quite a lot of different problems can exist, and also all these problems should be solved depending on the strategy that we choose for the decommissioning. It's immediate dismantling, deferred dismantling, and internment, as we already discussed. And actually, if you look on the international experience, not only in Russia, but the international experience in the decommissioning projects, we will see that only 35% of the project they are successful. That means they're finished in time and with the cost that was initially estimated. And the reason for these numbers, that there are three main reasons: that there is no clear understanding between technical experts and management. Experts, it is a miscalculation of the decommissioning due to the absence again of some long-term program. So you have no sufficient infrastructure for this, and you can probably miscalculate some steps that you have to take to meet all the criteria that have existed in the countries. And also, it is sometimes the absence or misapplication of the project management to this project. There are some guides and documentations that generated by international organization or by national bodies that aimed to solve these problems. So it's like guidelines for application of different approaches for decommissioning, and the main idea is to decrease the zone of uncertainty, because the decommissioning project, as we saw from the previous lectures, it is very long-term operations. And of course, when you are planning decommissioning, you have some certain schedule, this calendar plan, but we always have uncertainties, and we either can reduce the project cost if we during the decommissioning can apply some like new technologies, or we can reduce time for some operation, or we can increase this project cost due to the miscalculations, initial miscalculations. If we didn't take into account some risk, or we misinterpret the possible risks, and we didn't plan the actions due to this risk. So this zone of uncertainty is can be very big, and the idea of the project management also so includes also the ways to decrease these risks. Okay. There are different basics approach for project management that are also developed by either international organizations or by some national organizations. They develop their own programs, own educational programs. There are some professional organizations. You can see the list of them, and there are two main basic approaches to project management that can be called like a process approach and competence approach. In the first approach, the process model, the theory of this project management suggests that all the project can be divided by the processes, and you divide all the procedures by these processes, and then you can combine them back like in tomography, when you slice an object by pieces and then take the model back again, that object. And the competence model based on the approach that there should be the key specialists that are involved in the project with relevant competences, and they organize all the work. So it's a bit different approaches, but the main idea is the project management, of course. So there is an example how in the process approach in this PM book, divide all the processes are divided by different groups. And in the competence approach, again, this international professional organization, they exist in quite for a long time, and you can take the courses from them. So about our master degree and what we thought when we started it, that during the education, of course, like in any program, we build some competences for the students, for people who will finish our master program, and these competences mainly based on the um, uh, technologies that are used in nuclear fuel cycle and the decommissioning technologies. We focused also on international experience when we organize the work during our master program. We initially planned to build a teamwork between the students. But it was not always successful because, for example, now in our second course we have only one student, so it is very difficult. Simona is our student, so it is quite difficult to organize a teamwork with one person. And as a final project work, we are dealing with some real applications of some technologies for a certain task. And we looked, of course, through the different international experience for decommissioning, for education in the field of decommissioning. We looked on some short-term courses, on bachelor degrees, on master degrees, on doctorate degrees in different universities, institutes, research centers. Also, there are some collaborative centers for decommissioning, and we look through in the program to understand what we would like to do and what we can to do in this international society. So first, it was our project together with the Terra company of Rosatom Group. We organized this master program for managers, for real managers who are working in this company, and some of them they had background in physics, only two of them. And other people, they didn't have any natural science background at all. So they are international communication specialists or economists or some other specialists. And we built this program from 4 blocks, as I mentioned also, that we give them the basic course of radiochemistry, of interaction of ionizing radiation, detection of ionizing radiation. Then there is information about the nuclear facilities, including nuclear fuel cycle facilities, how to how different nuclear power plants are designed. Then there are methods for technologies for decommissioning, and of course some managerial competences. Some of them were already certified managers, so it was different programs for different people. Some were more focused on cost management, some on project management. So it's a bit different, very different for different people. And Yeah. The general structure looks like this. Again, it has information about all these technologies, let's say, and also some legislation information, normative base, Russian normative base, international recommendations of different organizations from IE, NRC, etc. And also it was very interesting course for contract and pre-contract activities. Further, it will be some detailed information about the different courses. Of course, on decommissioning started from the information about the nuclear facilities. We started, of course, with the introduction to nuclear fuel cycle and explain the design of different objects of the nuclear fuel cycle from mining, enrichment, fuel fabrication. A big part was devoted to the design of nuclear power plants, because most of the objects for decommissioning the entities and important for entity decommissioning is the management of spent nuclear fuel with further radioactive waste management. Then it is course on decommissioning technologies with the decontamination technologies, different types, chemical, mechanical, physical decontamination technologies where they can be applied for metal surfaces, for concrete surfaces, for other surfaces, for soil remediation, maybe. Then it is a method for dismantling that we very shortly overviewed during our lectures, and also for some basic information about the demolition technologies. Then it is the radioactive waste management with the classification, normative base, what we are doing for pre-treatment, treatment of the radioactive waste, conditioning, transportation, etc., etc. Then one of the important part for these students was to understand what are the nuclear facilities that are present in different countries, because the people, these managers, they are not only managers for projects, for decommissioning project, but also the part of them responsible for marketing, for introduction of, let's say, Russian technologies to the international market. So it is important to understand in which countries what are the objects that exist there, and what is also the differences in regulations in these countries, how they build their normative base, etc., etc. Yeah, and of course, maybe in other direction, the basic information about the actions and recommendations from the international organizations, so like supranational. It's not a really regulation. It's recommendations of different international agencies. So, and then, of course, as I mentioned, as far as one of the problem of the project in decommissioning is the cost estimation, it is necessary to give the basic information on how what are approaches can be used for the cost estimation of the project, because these approaches can be different. And one of the part of these exercises was the real Excel table where they put the numbers and calculate the cost of the decommissioning project. Of course, it is course on the project management, also together with our Russian certification organization. We are now planning to do it like mandatory for our students to perform this certification for the project management certification. So after this course, they will, after finishing our master program, they will have not only the diploma of Moscow State University, but also international certificates as a project management. Another route was developed for people, not only for managers, for students who already have a natural science background, and it was supposed to be different for them, but we saw from our present experience that people with natural science background such different in this background, and we still have to give them the basic courses on radiochemistry, and in some cases in chemistry as well. The idea was again that these people already have good knowledge in one technical discipline or field, and we give them more broader disciplines in project management, in stakeholder involvement, in some communication technique. So it's like a T-shaped professionals but again, as a final stage, all of these people have to have like a basic technical expertise, understanding on how different techniques are working, where they can be applied, and then they have this managerial competencies to perform the good project management. We for our Russian students, we organize practice in Rosatom companies. We are trying now to organize it also for foreign students. It looks not so easy, especially now due to the COVID. But also we try to organize the technical tour to one of the Rosatom company within last school and this school, but still due to the restrictions, due to the COVID, we cannot do it, because even so half of the personnel are not allowed to enter. So they say that we cannot invite our people. So sorry, we can for foreign participants it is even worse. But we hope that this will finish and everything will be okay. And yeah, the third route is like the product of this master program that we are developing like a short-term courses or like a models, small models for 2 weeks, let's say, education, depending on the course. It can be 1 week or 2 weeks of training, and depending on what the specialist from the company or from the university needed, they can choose different models, different blocks, and this certificates of education. And that is more important, not the certificate, but the information, the knowledge about these topics. Yeah, this is all for this presentation. Thank you. And that I also would like to mention that our first program was organized together with this 12 company, and it was very interesting experience. Thank you. Yeah. Mm-hmm. Yeah, for sure. Yeah. Or at the end, you can copy it. We certainly will put all the presentation in the cloud. Yeah.
Can we just share the link?
Yes. It will be shared link. Yes.
Very interesting.
Yeah.
It's not my students, but we will talk
Mm-hmm.
about that later. Okay.
Yeah. So if there is no question, then yeah, Home. You would like to ask something?
Yes. This, I understand correctly, many nuclear reactors in the last 30 years have been worked globally. But they were not producing such feature about decommissioning.
Mm-hmm.
In practice, decommissioning should be a part of the designing process, or
Yes.
designing should be made keeping decommissioning at the end.
Uh,
The first question. The second question is, if my whole nuclear FPP will be 100, for example, 100 Google I invest, how much percentage should be dedicatedly get for decommissioning?
Yeah.
Two questions.
So the first question, I personally believe that the plan for decommissioning should be designed to the very beginning. It can be changed due to the development of the new technologies, etc. But at least even let's imagine that the technologies will be the same. You will already have a plan what to do and how to do it. So my personal belief that yes, so we should plan the decommission from the very beginning. But very often when you look on the project documentation, it is only one sentence that the decommissioning should be planned, let's say, for 10 years before the shutdown, and that's it. So that is the only plan for decommissioning for current entities. So that decommissioning should be planned before the shutdown. And for the cost or for decommissioning, different approaches, but the main approach for new facilities at least that you put a price for decommissioning in the product that you produce into this facility. If it is MPP, you put some tax for decommissioning in the price of electricity that is produced. If it is some kind of medical facility, you put some tax for included decommissioning in the price of the medical procedure. So the acquisition of the facility, you collect money in the special fund, and when the facility shut down, you take this money from this fund.
So the design phase or in operational phase, you don't have to concern to have a specific amount of money.
No. During operation, you collect this this money and by this tax. So you should estimate this cost correctly with the prediction of the future cost, because, for example, in Russia we have for radioactive waste disposal or storage. Now we have a special organization that is called National Operator of radioactive waste, and they have their prices that you can look in the internet. So for this year, the price for storage or disposal of such class of waste is 1 million rubles for 15, for example. And there is a price already for future years. So, and you can extrapolate it for more or less. So you have these numbers, and you have to correctly estimate the cost for future decommissioning, radioactive placement, etc. And put the small tax in your price of electricity need to
This aspect also very good harm because a lot of things and many things are well organized in a way unpredictable. Almost, I won't say zero, but nearly zero experience of them, which is a very uncertainty.
Yes, yes. For this, there are several international organizations starting IAEA, NRC, and some other smaller organizations who are specialized in these questions. And these countries, they can consult with these organizations, of course. It is not so. It is always a responsibility for the country, but you can always ask questions and take advices from many other international organizations. That's why Vladimir Mikhal yesterday also showed that there is special platforms and websites that are created for this communication between specialists and non-specialists and specialists. It is very important.
So, how much does it cost? I'm planning to apply. Does it have some discount or not?
For master
Yes, I'll start with this radiochemistry. I can apply.
And we have a fixed price that is established by our rector, not rector, but the scientific council. It is 500,000 rubles per year.
Per year.
So for the 2 years, master program will be one.
There is a discount for overseas students.
It is fixed and we cannot check. It can be watched.
Any job guarantee, any position guarantee after graduation?
Sorry?
Any position guarantee after graduation? A successful
Scholarships, for us, it's a difficult question. You know, there are some quotes to students, but these quotes, they of tax from Russia, but our university is out of this system. So we are like independent. and we cannot apply that to schools. So there can be some fundings for students. For example, now we have students who got the scholarship from Turkish government. We are also trying to make our administration because this tools can be accepted also depend on our administration. Against the school because they don't want
Thank you. So now we have a break, and we will start. We will continue at 2. At 2.
You have more participants.
Yeah.
Online.
Yeah.
Good. Thank you. Okay. So you see this table. In this table, these are low intermediate level waste operational. That means exactly which form is 50 cubic meters on average. But these are numbers from nuclear power plants from Russian Federation. So you see here that in Russian Federation, they run nuclear power plants with PDR reactors. And these, there were, in the past, it was in Chernobyl operating. So that's the table because I'm not young. So at that time, it was operational in Chernobyl. So that's in Kursk, that's Russia, that is now Ukraine. At the time, it was Soviet Union together. And this is, in the past, St. Petersburg was Leningrad. And even now, they call the nuclear power plant Leningrad nuclear power plant. So the name is correct. So you see some of radionuclides there. So cesium, that one, which is 137, is 30.17 years half-life. Shorter, it's 2 years half-life, 134. And then some cobalt, a little bit volume 239, but not everywhere. So not here, not here. But you see here the order of the number, so contamination and becquerel per cubic meters. And in this, you see some of them are higher, some lower. So we need, this is an element of characterization. And characterization also means characterization of other materials that are dissolved or present in these contaminated waters. So for example, you can see here the line about the pH or the total salt content. So it's kilogram per cubic meters, means gram per liter. And you see that it's also different, and also what kind of cations and ions there. And then here from other in gram per liter paper. So this is characterization, and it's absolutely necessary if you want to even start thinking what to do. Even for the discharge, you will be asked about the composition chemical and, of course, presence of radionuclides. And moreover, for the treatment, you must know what you are working with. So characterization is the first step. So that's it. Characterization is done, and no way we have to treat the liquid radioactive waste. So the treatment, it is defined in such a, when we say treatment, it means that we are going to achieve these generic objectives. The first one is to reduce as much as possible the volume. It's very costly to store, to transport, to dispose of. So volume is better to make it as small as possible. The second one is to remove radionuclides from the waste. And the third is to change the composition. Sometimes it's necessary, let's say you have a very aggressive, very corrosive solution, and you need to change the composition in order to be able, let's say, to do something later with this material. So, and this is three generic purposes or objectives of treatment. They are the same for solid and liquid, the same. My lecture is about liquid, but for the solid is the same. So to reduce the volume, to remove the radionuclides, and to change the composition, if let's say this is a burnable, so fire hazard, then to eliminate this hazard, so to change the composition, to make some oxides, so to apply, let's say, incineration. Okay, so for the liquids, in most cases, the treatment of these streams, it is like in this picture. So it's to split our aqueous waste, so on the basis of water, using some technology into a large stream, which is almost clean. So theoretically, no radionuclides here, and to obtain as small as possible another stream. So yes, we change because we run it. So this is how schematically we can represent the work of liquid waste treatment technology. And how many people do we have online?
Only one.
Only one. Okay, it's also good.
The screen is not working. I don't know why. So
For him.
Yeah, for him.
Okay, so we need to keep this one.
Yeah.
Okay, let's keep this one. It's a little bit smaller, but not too small. So I guess, and then you have all these slides.
Now it's thank you.
Yes, so let's, so then, no, that doesn't work, this one. It doesn't change the face.
No. Just click on.
Video.
Right click time to work.
You think? No, it doesn't. So now I have problems. I think maybe here. Let me try.
Click on.
Oh, okay, so here is working with the mouse. So colleagues, once again, so it's schematic of how it works, and for treatment of liquid radioactive waste, we use the parameter which is called, the name is decontamination factor. So it's defined through this equation. So you take the activity or the specific activity of the initial waste stream, divided to the radioactivity of this almost clean water. And because there it's a very small content of radionuclides, typically you obtain a very good decontamination factor. So this number, if it is very large, that's the best technology. If it is small, not so good. So decontamination factor and its definition, it is here. Okay. Oh, now it's working. Very good. So let's now look to the treatment technology. So here it's a schematic. And the aim of this scheme, which is complex one, we can go through it, but my aim is to just to tell you that although there are here basic 4 technologies, so chemical precipitation, most developed, then ion exchange sorption, number 3 evaporation, and number 4 membrane methods, typically at water purification or liquid radioactive waste treatment facilities, workshops, etc. The real technology of steam is much complex. It's not just just one vessel to do all the job there. So you see many apparatuses, and the purpose of each of them is to do its maybe smaller job, so that altogether that schematic that I showed to you and split it into streams will be done with a good decontamination factor. But the most important technological approach for the treatment are these 4. So chemical precipitation, then ion exchange sorption, then evaporation, and membrane methods. And it's a kind of the trend of using on more and more membrane methods, although they are all used. So it's not something like a transition from the previous to this one, which is maybe better. They can be better depending on the task, on the availability of many things, etc. So here I have several tables that are very useful. From you, non-readable, I'm sorry, but they are, let's say, these tables that are here are actually the description, the overview of these technologies, these most important features and limitations, and the most important information about this technology is in these tables. And other things that I put in the presentation, I got 64 slides, are, to comment on these things. So here, the table, it's about, at the moment, 3 methods. So the first column is chemical precipitation. And then the second one is ion exchange. And the last column is evaporation. And then another slides, other methods. So here, it's about the liquid radioactive waste characteristics. So for example, for the chemical precipitation, it says that is not sensitive to highly salt laden or content solutions, which in some cases is the case. Ion exchange is suitable for low suspended solids content and low salt content. So it's just opposite. Evaporation, low detergent content required, not suitable for volatile radionuclides such as tritium. So this information is very good. The second line is exactly what I defined to you, decontamination factors. So I will not bother you more with reading here, but for decontamination factor, it's, and I'll repeat that, it says that chemical precipitation from 10 to 100, but can be for alpha radionuclides even 1000. For ion exchange, from 10 to 10,000. Average 100 to 1,000. So it looks better. Evaporation looks even fantastic better because it's from 10,000 to 100,000 times. So you have, after the utilization of evaporation, 5 order of magnitude lower content of radionuclides, which looks very good. But they have also limitations and so on. So it depends on these things, and including also the cost. So I have a slide to show it to you. So it was not all. You see, for the membrane methods, the tables are so long that even I was not able to put them on one page, let's say, in one slide. So the next is also membrane method. So membrane methods are divided into several, let's say, sub-methods. So the first one, the upper line, it's microfiltration. It is when you remove fine particles, and these can be not smaller than 5 micrometers, other will pass through these membranes. But no high pressure required. And then you get ultrafiltration. In this case, you are able to work from fractions of micrometer up to 100 parts of micrometer. But they require pressure. That should be up to 1 megapascal. So that means something like 10 atmospheres. And then I'm moving down, nanofiltration. So nanofiltration suggests what it's about. It's sizes about nano. So it goes to 1,000th part of a micrometer, but requires higher pressure. So typically it says here 1.4 megapascal. And it is not all. There is the most powerful method in membrane methods, which is called reverse osmosis. And that method removes practically even ions and small molecules, even small, larger, of course. So in some cases, this reverse osmosis can be used instead of evaporation to obtain distillate, to make distillation, to obtain deionized water, which is used in laboratories for different tests, etc. So instead of using the evaporator, distillation, reverse osmosis is used, but requires high pressures, because otherwise the water doesn't want to pass through these membranes because the pore size are very small. So needs high pressure systems. So these were tables with generic information about main 4 methods used. And these methods are used, in purification of the water by other industries, not just for waste treatment. So if by chance you will not work for nuclear industry, you can find useful this information in other areas of applications. See? So we move. So the selection, when you select which method to use, or maybe what combination of methods, then you need to make a decision, and you are looking to many factors. So first is characterization. And then you look to discharge requirements. So to what degree, what the continuation factor you need. Maybe just 2 times decrease the content of radionuclides and the job is done, but maybe you need at least 100,000 times. So available technology and their costs, conditioning of concentrates. So this small stream that you obtain with radionuclides, what to do with it? It's still liquid. So it requires some conditioning later. Storage and disposal of the conditioned concentrates. So that this information typically is analyzed, and then you take the decision how to go with the treatment method. A couple of, to diverse the publication of facilities for treatment of liquid radioactive waste. So apart from one that is a small one here. So I was involved in operation of these facilities. So they are in mobile. So we have modular or mobile facilities that combine some of these methods, and then they work. And one interesting, which was through IAEA, International Atomic Energy Agency, distributed to many countries. So if is anyone here from Iran, then it was submitted to a nuclear research center in Iran to work there, into Syria, to Uzbekistan, to Serbia and Europe. Of course, it's used in Russian Federation. So this is a small mobile modular facility, and the parameters of this facility. This is for small users, because the capacity here is 300 liters per hour only. So if you have several cubic meters, then it's perfectly good. Because of that IAEA, so it's manufactured, it's by Rosatom. The institution is Radon, but this is a part of Rosatom. And through IAEA, through technical cooperation project, it was submitted to these countries to help them resolve the problem with liquid radioactive waste. So here the important parameters about requirements for power supply. It's 1.5 tons, the total weight of all this facility. The pressure 0.45 megapascals of 1.5 atmospheres. It works from 5 to 40 degrees. So it's important if it is going to be used. Before entering into more detailed description of these technologies, 4 of them, there is a so-called pretreatment. In reality, this pretreatment, it's a part of the facility. But it is, by definition, by the terminology, you see here, it's not treatment, it's pretreatment. It is because the objectives of treatment are not to reduce the volume. And pretreatment is something which does not allow to achieve these objectives. But you need to have this pretreatment, otherwise the treatment will not work. And because of that is named pretreatment. So let's say you have a large piece and you cut it into parts because it's too big. This is pretreatment because it is still the same. Volume, everything is the same, just the size change. So then this cutting is termed pretreatment. In liquid radioactive waste processing is the generic word. Pretreatment is when you do sedimentation for some coarse filtering, so some oil solvent removal so that the apparatuses will not be poisoned and destroyed. Change a little bit composition by adjusting the chemical composition. So these are the examples. So in the tables that I showed to you in membrane methods, filtration was not there. So you know, in popular language, we say that we are filtering, let's say, something like the vision of this mask, we are filtering. And again, you know, the people, when they were introduced, they immediately started to complain and to say that the viruses will pass. That's fine, they're so small, but of course they should pass. But filtering is not, you know, that you need pore size smaller than the size of virus. This work as a medium which capture nevertheless viruses, because they are, you know, moving, you know, this Brownian motion. So if it is thicker, then sooner or later these viruses will be caught by the material somewhere. Sorry, we will deviate too much. So let's not enter into this later, because of course to me is also that I have a big lecture about, because I prepared in the agency a handbook on gaseous systems. So to me it's also interesting, you know, this thing. But let's stay with the liquids. So if it is in the liquid question asked, if it is in the viruses, you will go too far away. So I see in the auditorium some questions, so please, maybe later. So colleagues, filtering in liquid radioactive waste treatment means something when just a layer of sand or something very coarse is used. So this layer, you know, is capturing something really big, you know, can be some dirt, something massive, and then it is filtered. And this, you saw microfiltration, ultrafiltration, nanofiltration, reverse osmosis. This is other thing, it's not filtering. Okay, please.
Sir, here is because the medium is unlike the gas. Here the medium is liquid. Here there is no Brownian motion, rather sedimentation, mostly because of gravitation.
Yes, this is gravitation.
So
it's okay. So wait a little. Be patient. I have other slides. So, colleagues, so these things which are called, you know, pretreatment. So here more explanation about that. But in pretreatment very often are used for filtering. So this is still pretreatments, these kind of cartridges. So there is like a bag, which is like a mesh, and the contaminated water enters from inside and then passes through this mesh into outside of this bag. And the dirt, these things, they are captured inside of this cartridge. So this apparatus does only pretreatment. It doesn't reduce the volume of the liquid still. It is just used in front of all other apparatuses, can be evaporation, ion exchange, and so on, microfiltration, in order to keep them working. So pH adjustment can be used. So you change a little bit the pH, and then you are able to force some of the radionuclides to dissolve, or just opposite to be amenable for the precipitation, and so on. So pH is also adjusted, and the objectives of treatment are not yet achieved, but we must do that in order to protect the next apparatuses. So here is information about here. Can be oxidation when we use very often, my colleagues, I'm myself not an expert, let's say, in water treatment systems, so my information is based on my collaboration with my colleagues. So, but I know that potassium permanganate, which was available in the past everywhere in pharmacy and so on, it is not anymore, because it's a component of gunpowder and so on, so it's for terrorists dangerous. But some addition of permanganate immediately oxidize everything, and then the next treatment processes work better. Okay, so can be even opposite, reduction rather than oxidation. So these things are applied in order to enable a real treatment, and I'm starting this precipitation. So the principle of this method, one of 4 most developed methods, is to use an insoluble material to remove the radionuclides from the liquid waste. So majority of precipitation methods, they use metal hydroxide flocks under neutral or alkaline conditions, and then they remove the radionuclides from there. So the mechanism can be direct precipitation or just co-precipitation. So for example, you have some strontium in your water, and it is content so small chemically that you organize precipitation of, instead of strontium, barium. But since they are chemically similar, strontium will go together with the flux of barium sulfate, and because of that will be removed. So the mechanism in co-precipitation, you have this carrier, this flux, so they are swept together with the precipitates from the solution. So several stages are used. The first one, it is when you add to your liquid radioactive waste a chemical reagent, this hydroxide, or you adjust the pH in order to force precipitation in the liquid. Typically, when you do it, the schematic is shown in the picture there. So you discharge some chemicals into your liquid radioactive waste, and you are interested to have a good distribution of this additive into your liquid. Because of that, typically in the apparatuses there is a mixer, and you intensively mix everything for a short time in order to get a good distribution of your additives in the liquid. Then the chemistry starts to work. So flocculation. So because of formation of insoluble components, they start to make these floccules, and the red dots on the screen are symbolizing the radionuclides which are in these flocks. And here, no mixing is needed anymore. So be patient, be quiet, do nothing, just wait and let the chemistry to work, because if you'll continue to mix, you will destroy the flocks and no precipitation will be done. So that's why it is said. And then the sedimentation happens due to gravitation, that it was noted in the room. And then you need to separate this layer. So separation, this layer from here. This is done by pumping from the upper part, the liquid, and from the lower part. So then you have this lower layer, which is called sludge. And here is the description of the chemistry. And you see here that the number of, so the first column, ready nuclides. Among them, there is their plutonium, americium, cobalt, strontium, typically. And then the second, it's about all kind of chemicals. So let's say hydroxides, especially ferric hydroxides, oxalates, then they are added, and then the pH, and then the contamination factor. It's written there more than 1,000. So I'm not reading, but the information is here. And of course, that before doing that, you need to do some calculations and to know how much you need to put this one into the solution in order to achieve a good result. So you need a kind of knowledge calculation before doing that. How it looks like, it can be very simple, like in this schematic and in the picture. And these are taken from IEA publications on modular and mobile facilities. And I noted to you that so this is where actually the chemistry happens, precipitation. And you see here that there is a pipe which allows to pump the liquid from upper part or lower part of this vessel. And there is also a mixer which does initial mixing of the chemical additives into the liquid. Okay, so I should show you this one to you, but it was there with the schematic, which is important. So I am moving to the next one. The next one is ion exchange sorption. So this process works very well when the salt content is low. So low can be, let's say, half of gram per liter, like in many drinking water. So not too much salt in the water, because otherwise they will, poison the ion exchangers. So the schematic is shown here. So you have here a kind of ion exchangers. Let's say here it is shown like sodium. It is kept here to some groups in the ion exchanger, and the water enter and the calcium there. It is exchanged with sodium. So on exit we have the water with sodium. It could be there cesium, radioactive. Then cesium will be kept here, and here it's sodium, which is good, no radioactivity. So the work is done on purification. This type of technology apparatuses that can be operated in both batch. So when you pour into the apparatus, the one batch, then wait, then discharge, go to the next, or can be continuous mode, when very slowly the water is passed through the ion exchanger and it operates in a continuous regime. There are many ion exchangers, and many parameters should be investigated before selecting one and another. So we have to look on the sorption capability, how selective is it. Kinetics can be slow. If you are interested in a higher capacity, then we will look to an exchanger which was quicker. In our case, radiation stability can be an issue if the radiation levels are high. Hydromechanical durability is said, because during passing of the water, all these granules and so on, they are moving a little bit, shaking, and they can be destroyed by mechanical friction in between them. And of course, availability, these things are also important. For ion exchange, it is used an important parameter which is called the distribution coefficient. I think I will not bother you very much, but that's not the same as the contamination. So here is the definition, because it is used in some tables. So here is the list of commercially available ion exchangers, solvents, and it starts with organic ion exchange resins. These are the materials that are most frequently used everywhere, both in civil and nuclear industry. Organic ion exchange resins. There are also natural materials like natural clinoptilolite. I will show you some examples from there. There are very good by the parameters, synthetic zeolites, aluminosilicates, silica gels, etc. So you see, it's a long list of these commercially available ion exchanger and sorbents. Okay, so the example that I promised, so this is from United Kingdom, from Sellafield. So they use in Sellafield to remove the cesium and strontium from the liquid radioactive waste stream. A part of it in the past was discharged into the sea, into the Irish Sea, and that was a story in the past, etc. But it was introduced the method of purification of this radioactive waste stream, and they use clinoptilolite. This is a natural zeolite, which is imported into the United Kingdom from United States, from Mojave Desert. They have their large deposits of this clinoptilolite. So it's not only there, but this is an example that I got. But they also use synthetic aluminum silicate zeolite for removal of cesium from fuel storage. So if you store for a long time, then gradually the water there, which is shielding everything, and you can see everything, etc., becomes more and more radioactive because gradually some diffusion occurs, etc. So in this pond water with ethmognosides, oxides, this synthetic zeolite is used. And so it's just to present an example. So these are the tables with these distribution coefficients. But the clinoptilolite, you say here, it's many natural, it's not just clinoptilolite. So there are many. It's in this part, and the upper part are these ion exchange resins, but these are Russian, let's say, made ion exchangers that are available commercially and can be purchased and used. So stability of ion exchangers is very important, and both chemical and mechanical I already explained to you, but also chemical, because the radioactive waste stream can be with different. You remember the first table? I showed to you the pH, and it's different in different places. So if your ion exchanger will be very sensitive to the pH, you will need, to adjust the pH. Otherwise, it will not work. But it's better when it's more stable. The interval is larger, so and so on. So stability, it's important, chemical, as well as mechanical stability. Okay. The apparatuses can be in the water, which is contaminated. We got both cations and anions. So because of that, the ion exchangers can be which will capture anions and can be which will capture cations. They can be placed in the same apparatus like here in this sheet. So you will have a layer of ion exchanger which is for anions, anion exchange resin. And here it's cation exchange resin. Or can be two such apparatuses in order to if needed, to capture both anions and cations. Okay, so here it's about to pay attention that if the content of salts is high, it's 1 gram per liter. This is typical. It's not something very strong. Typical. Then the reason of this limitation may be even obvious, because if you have too much salts in the water, they will contaminate, and instead of cesium, the ion exchanger will capture, these ions from non-radioactive components. Okay, so we move to the next one, which is evaporation. At nuclear power plants, this is the method which is used everywhere, and it is very energy consuming method. You need to evaporate the water. To evaporate the water, you need to use, it's written here the number, 6.6 to 10 raised power calorie per cubic meter. And the theoretical consumption is written here. So a lot of energy, because you need to evaporate the water to organize the phase transformation, to make the vapors. At nuclear power plants, it is so much energy generated by nuclear reactors. That is what to do with it. It's too much. So because of that, all nuclear power plants easily use this technology, which is very good by parameters. So that shows how it is organized, and you have a lot of knowledge. But for the students, university, and so on, I added here, this part, because after evaporation, you need to condense back the vapors, which are almost clean water. And then there is a loop which allows to work the condenser. And this loops is this, large cooling towers. In many places, cooling towers are used, but they are not directly connected with the loops of the reactor. So that's for generic public to extend them that there is absolutely no contamination in that water of the condenser. Okay, so here are typical parameters about the pressure, 0.5 megapascal, temperature in this big apparatuses, it's about 150 degrees. So how they are organized to evaporate the water and then to condense it back. And here it is written about the decontamination factor, so can be million times, this small number here, well-established technology, high volume reduction, suitable for a large number of radionuclides, so maybe the tritium is a problem. But even the tritium, by the way, it is because it's a little bit heavier, so with time, if you many times evaporate condensate, so the remnant, let's say, you have a little bit more. There is a very small difference even for tritium. So it is also emphasized here that in some cases it is used in two stages in order to concentrate and then again concentrate even to higher salt content in the obtained residue. So here are some real parameters of real apparatuses, like that one which is taken from Slovakia. Is anyone from Slovakia? Oh, very good. So that's from Bogunica. So they use, it is used everywhere, but this is just as an example, let's say, where it's given the parameters of capacity, the combination factor. Here it's 10,000. So it's something average, which is counting all the radionuclides, and sometimes in the waste stream we got iodine, which is a little volatile, let's say, so can be lower than these millions. So nevertheless, is 4 orders of magnitude, it is decreased the concentration of radionuclides. So it's written here about suitability. It's expensive compared with other treatment processes, but at nuclear power plants, it's easily affordable, and it is used everywhere. So I finish with that. The last method, it is for membrane processes, and I put here as a basic document this IAEA publication, which is fully dedicated to membrane technologies for liquid radioactive waste processing. And it was organized, this publication, because there is a trend of using membrane methods on larger and larger scale at waste processing facilities. And this slide shows that if you have a membrane, you need to force somehow the water to pass through the membrane, because the membrane has very small pores size or capillary channels, and because of the surface tension, you can keep the water in a membrane, and in order to pass through it, you need to apply, let's say, a force, but you can apply not just the pressure. So here delta P, it's written, it is when you apply pressure in order to force the water to pass through the membrane. And you see here that it starts with filtration when actually you don't need much force. Gravitational already works. Gravitational already works. But if you go to the caustic space, no way. There is no any force present to force the water to pass through. So maybe you heard about Darcy law and these things, so the high column, lower, but I'm not entering into that. And then microfiltration. So the pores, you remember they go 5 microliters and larger. And then this ultrafiltration, but with high pressure. And then nanofiltration, even higher pressure. And the last one, which is even for molecules, requires the highest pressure. So here it's for pressure. It can be membrane distillation. Then you will use the temperature to force the water to pass through. it can be the so-called electrodialysis. So electrical current will force the cations and ions to pass through the membrane. So will do the job. Or can be like in so-called reverse osmosis, the difference in the concentration of salts. I will show that in the next slide. So the explanation will be there. What is meant under that? Okay. So here it's a schematic. So let's say in this part you have contaminated water, and when you use microfiltration, you capture things. It's written here larger interval range. So from 1.1 to 10 micrometer. Then ultrafiltration works in a smaller, so 550 nanometer. Nanofiltration half to 5 nanometers. And reverse osmosis, you capture practically everything. Only purified water is able to pass through. Let me check here. No way to you to read. Sorry, but yeah, I can on the screen here a little bit. Here it's written what kind of pressures you need to do. And in this case, you need some 5 to 10 megapascals, so can be, you see, 100 atmospheres, high pressure. It's not difficult to have, a pump and to organize such a pressure, but we are working with ready materials and then these things. Okay, so we go. Here it's about, you see here, first column separation process, then what kind of membranes are used. So for microfiltration, symmetric microporous membrane. For, let's say, reverse osmosis, asymmetric skin type membrane. So they keep everything inside, and you need very high pressure to force the water to pass through. The method, as it was shown in the picture there, and a range of application. So for the reverse osmosis, separation of salt and microsolute from solution. So just water passes through. Okay. So that one I also promised to you, and that one can be useful plot if you are looking on economy. If you have large volumes and you want to purify this water or to use it to process your liquid, you have maybe 1,000 cubic meters of some contaminated waters, which is ready to waste. And if you apply one or another method, here is as a function. This is the content of the salt. So here it's very low content, like 1 gram per liter, and here is 100 gram per liter. And the method which is not sensitive to the content of the salt, so the price is there on vertical axis. So for evaporation, which is named there distillation, doesn't matter. The same high price because you need a lot of energy to evaporate everything. So it doesn't matter. It's here or there, you will pay all. So then you look, these methods are working better, much cheaper. It's 10 times cheaper. And if you have 1,000 cubic meters, it's a lot of money. So then perhaps you look to this method. But we are looking now only on the price, not on other things. So they are also important. So here it's electrodialysis. Here is ion exchange. That one is reverse osmosis when you apply pressure, so pumps. So you see, up to quite high concentration, they are cheaper. At nuclear power plants, the energy is redundant. So but if you are in a facility which you don't have supply, electricity is expensive, you need to pay, then you have select other methods, and will not go to expensive things. Okay, so the next one is to explain that there are two types of filtration. So it's like direct filtration and cross flow filtration. And the schematic is shown here. So you put in front of your screen something, and everything which is passes, it's just directly filtered. So this is conversion filtration. The cross-hole filtration, it is when your stream moves into this direction, but through the membrane something is passing, and this is called cross-hole filtration, and it's important. It's important because the membrane method typically works in this way. And you are able, to wrap your membranes to have a very large area of working apparatus, which is then inside, it's wrapped inside of a tube. So here, as a function of a size and micrometers, it is shown again this, you see, filtration, microfiltration, nano, reverse osmosis. So reverse osmosis for small atoms, etc. And there in upper part, you see that I provoked to you with the viruses. They are there by size. And bacteria are larger, so again, because we are now in the technology which is using membrane methods. So here it's a kind of repetition of this schematic of what is captured and what kind of the pressures you need in order to do that. So it's a kind of repetition of the parameters. And for reverse osmosis, this slide, it is to explain what it actually means, reverse osmosis. So the osmotic pressures appears naturally when you have a membrane. In this picture, maybe you will see here, let's say this is the membrane. And you have here a material with a very high content of salts. Then by osmosis, the water will be, like sucked inside of this high salt containing material. So in reverse osmosis means that we will apply the pressure to balance this osmotic pressure and even higher, so to reverse the osmosis. And because of that, we need here quite high pressures to force the water to get out of the salts into this part of the apparatus. And because of that, the name reverse osmosis. And by the way, just for your generic information, because many of you are working in laboratories and so on, don't drink deionized water, because the deionized water will make a very bad job to your organism. It will suck good things from your organism into this deionized water. You understand me, no?
Yeah.
So if you drink that, let's say, several months, only deionized water, you'll get ulcer. So you see, clean water, absolutely clean water, becomes dangerous. Okay, so that's about the reverse osmosis. So here it's about advantages and disadvantages of various membrane elements. So there are many possibilities. Here it's a photograph that shows that inside of like a straw, there are many channels. So the water it's pumped from there and passes through the walls, and so because of that, some of them are flat. So the water passes through a flat membrane. Some of them are tubular, like in this photograph. Some of them are spirally wounded, can be hollow fibers, and they have advantages and disadvantages. And to read will take a long time. But schematically, it is shown here. So you can wound, so to get a very large area. And this is, you see, I put the arrow here. So this is for tubular. This is a tubular amount. So the packing density is shown here. The energy utilization. Can you clean or not these membranes? Because they this time, of course, are collecting all the stuff from the liquid radioactive waste and stop working. So you need somehow to clean them, or otherwise you get this secondary radioactive waste. Replacement material, common applications, and spirally wound membranes like in this picture. So packing is very good, of course. So you see here, you can have a very large area because you wrap everything in a such. So energy utilization, cleaning can be difficult because it's blockage, of this interspace. So replacement, you replace the entire element. polymeric membranes are typically used, and it is used, this method of in nanofiltration and in reverse osmosis on large scale. So it means large scale, so not only like nuclear industry. Okay. So an example, colleagues. I don't smile. An example, colleagues. So it's a short additional chapter. Here it's a publication. I worked for the IAEA, International Atomic Energy Agency, almost 8 years, and I was the technical officer for Georgia. And in Georgia, we completed a work on purification of 50 cubic meters of legacy liquid radioactive waste. So after I left the agency, then jointly with my colleagues from Georgia, so we published recently this paper in the Journal of Processes. It's open access. So you see here Georgi Nabakhtiani, Irma Georgadze, and myself. But I'm myself from Department of Material Science and Engineering, Faculty of Engineering, University of Sheffield. So I had enough time because during my work in the agency, it's so much to do that no way. So it's to demonstrate to you. Let's say this schematic shows how you process a liquid radioactive waste stream as IGC recommends. So it's a schematic that, sorry, difficult to read it, but you know, it says that you have the waste stream, you use pretreatment in this line, then physical and chemical characterization, then is waste suitable for clearance or not, and then treatment itself. And then here you will get secondary waste, concentrate, decontaminated liquor. So this is purified water. And then let's say secondary waste, you need maybe to treat it, maybe not. Maybe you can go directly to conditioning. And then transportation storage. And the water which is cleaned, you see if it's suitable for clearance, your regulatory authority allows you to do that, then you discharge it. If not, maybe it's released to environment as an exempt waste. So it's here. Here is discharge within authorized limits. So depending on if you are below the exemption levels, it goes this way. If not, you ask the regulatory authority, they give you permission looking what amount of the waste the radionuclides it's going to be discharged, and it is done this way. So in Georgia, we went this way as shown by these arrows. So you see not all the states where we used. So the secondary waste went directly to conditioning and then transportation for the storage. And for the purified stream, we were not able to release as exempt waste, but regulatory authority allowed to discharge within authorized limits. So the content was so small that was permitted to do. And what was the story? The story was such that in one of 3 underground tanks, it was found that they have these 50 cubic meters of contaminated liquid radioactive waste. And here are the parameters, the activity in becquerel per kilogram, how it was measured directly there in Georgia. So characterization. And then this is a thematic of facility that it was used there. The facility, I will show the picture, how it looks like. This is a scheme, technological scheme. So it was manufactured with the help of IAEA in Russian Federation by Rosatom, and then transported to Georgia and worked there. So here's the explanation, how it looks like, etc. So what kind of methods were used. So that was a utilization of just few of the methods, membrane methods. Colleagues, the facility itself, it is this one. So it was manufactured by Russians, by Rosatom, inside of 200-liter drum. Except for the pump, which was used, to pump. There are some pipes there were, and so on. And that was done intentionally. So these are some filtering equipment with this membrane method, with some sorbents, etc. It was designed in such a way that when we finish the work, all the secondary waste including some gloves, some pieces of contaminated material, were put inside of this drum and cemented. The slides were cemented in these drums. But one of these 4 drums, I'm sorry, just 3 drums, because I forgot already. So 3 of these drums are now there. This is conditioned waste. And one of these drums is this equipment, which is cemented and left for storage and disposal. So you imagine no need to transport back to Russia this facility. It was left as a waste there. It completed the work, and this is something exemplary that in some cases, when you deal with some legacy waste and you have one job to be completed in one campaign, such an approach can be a way of working. So it's not for nuclear power plants, it's for relatively small amounts, like these 50 cubic meters. So the references here, it works. So if you press here, it will go to the paper with the details. So conclusions are that the most frequently used treatment methods, technologies. So the first one was chemical precipitation, then we looked with ion exchange sorption, evaporation, number 3, and the last one is membrane methods. But typically they are used in combination. So can be one with another, can be precipitation and then ion exchange to polish and to make the water drinkable or something like that. So no, typically it's not just one, typically several of them. And also I put here some useful references. So you see this IE publications, including that one that the cover was shown to you about the membrane technologies. So with that, I finished lecture, and if questions, we have some 5 minutes for that.
Yeah. Thank you very much. Questions?
I have a question about water treatment in Fukushima. Was in the press, was a big issue that I don't know if it's only tritium in the water, but have you been involved, or if not, do you have an opinion about what can be done with this water?
When I was the staff member of agency who was still involved and worked there myself, I never traveled to Fukushima itself to work. So from the agency, I was not involved. But yes, I am reading and so on about that. So it was an issue. We tried to enter into this business with some scientific, through the university, to propose some of our methods. We actually tried to propose what to do with the filters, let's say filtering materials after purification, because they are accumulated and sooner or later this is radioactive waste to be somehow disposed of. So we propose to use high temperature methods to produce from these materials some ceramics, plus composite materials, etc. Not much successful, but it's still under application and underway. And now we have scheduled an online meeting with our Japanese, so it's a consortium. So University of Sheffield, together with the organization from Japan, we apply together with them, trying, to get some funding for our research. So that's research. It's to be used later by the industry. So it's not exactly what you asked about.
But what's the problem there? It's really a tritium?
It's not only.
Not only.
Not only.
But why? Why is it so complicated to filter, to separate?
It's not complicated. Technologies are known. In this particular case, the problem is volume. So they were pumping seawater, which already has salt content, 10 grams, 20 grams. That's what exactly in Japanese seas. But that was highly salt content water. And now this water is with radioactivity. So the problem of purification is much more complex, more difficult because of the salts. And it's not only tritium. Because for tritium, the discharge limits, everything is much easy. Content is higher, hazard is lower, so it's not only tritium.
So the problem is really the volume to treat it.
In this particular case, the volume is huge. It's huge. And then you produce many used filters, and they are also huge now.
Okay.
Do you know the volume exactly?
Sorry?
Approximately, do you know the volume of this water?
From the memory, I will not give you the numbers, but ask Google, he will tell you.
I think about 500,000 cubic meters. because
Sorry, it can be, but today,
really, Nine Sigma company sent an email to me because they want suggested research proposal to move tritium from water. So I aware about this issue.
so you would answer. Thank you.
Take my call.
But it is a very big issue in general because the tritium has the same chemistry with hydrogen.
Yes.
Any radioactive nuclide can be separated easily by using different nanomaterials and so on. However, the problem in the tritium is that it has the same chemistry of the hydrogen.
Exactly.
So we separate water from water.
Exactly. So
It is very-
how to extract tritium from the water, of course, is known, but it's expensive. That's the problem. How to make heavy water is also known, the technology and etc. So, but by the way, Russians proposed how to do it. I don't know how successful commercially are the Russians. I mean, Rosatom. So, ask Russians, not me.
So I have one question.
Yes, please.
So this was the real main problem was what our colleague said. Tritium is a very common scenario, but with respect to Fukushima is concerned, because of tsunami, the two factors which were of control, it was tsunami. So 500 is not a countable factor. Tsunami, which is along with its force, penetrative force, on high density and high pH. These factors has nowhere in the past people had experienced that how tritium along with this marine water with high pH and high density.
Yeah, and immediately.
No experience.
Yeah,
So
yeah.
many people simply provide their theory theoretically, but there was no experience.
But immediately after that, the IAEA amended
Yes.
many of you know this.
Analysis are done, but it's very difficult to exactly prescribe or presume that this was the region. It's impossible. Everybody has their own theories, but the parameter is density, pH, and tsunami force itself.
Tsunami is not anymore present, so
Yes,
now
so
it's not a question. That's the cause.
Yes.
And yes, yes.
But my question was about the aqueous medium. We did not deal with porosity and permeability. Does it play any role or it has no connectivity at all? When you deal with pentonites, for example, or UK, second US.
Okay, so other questions?
Sir, these are my questions.
Which question?
Porosity.
What you ask me?
Because I'm sending this.
The porosity and permeability. Does it have any kind of influence with?
Porosity of what?
For example, you took the pentonites, said that in UK,
Yeah.
which is.
This is no phenolphthalein, but this is a natural ionic changer. Natural ionic changer.
That's what I'm saying. Whether porosity and permeability plays any kind of role.
These are the parameters that belong not to the material, but rather to the system which is used. And of course, it's important. It's something which influences, of course, if you have a thick layer or a thin layer, and etc. So of course. Sorry, what the question is about? Not much understandable to me. So my impression is that you make some comments, but they are obvious. What you ask? What you want to know?
Whether porosity and permeability.
The answer is yes, but that's too little to say yes. Perhaps you want to know something more.
Yes, exactly how.
You ask how? In a way that if you have such a pore, everything passes through. If you have such a pore, nothing passes through.
With respect to ion exchange.
Yes.
Connectivity to ion exchange, how it plays a role. Does it play a role? If so, how? That was my question.
In organization of the work of ion exchangers, the material ion exchanger, it's typically made in form of some granules. So then these granules are packed in a layer. And then through this layer, it's passing your waste stream. So then you have the porosity of the layer, which is the volume in between these granules. This is one kind of porosity. but the material itself, let's say clinotillolite, it also has porosity. And this clinotillolite, it is selected in such a way that if you look at the crystalline structure of this clinotillolite, it has a kind of cage-like crystalline structure. And this kind of porosity is extremely important because depending on the size of these cages, you have selectivity. So let's say you can capture cesium and not capture strontium, or etc., etc. So all these things are very important at their level. So to me, it's not very much understandable what you are looking for and what you want to hear about.
I got it. I got something.
Thank you.
More questions? If it is not the case, so thank you again.
У них дальше практика, я что? Да, все здесь вырубать.